Start with the third section of this chapter, and we are going to introduce the idea, or the concept of electric fields. Okay, now if we have two charges next to each other, or within the range, A and B exert electric forces on each other. Now, for the electric field, we don't have actually, we shouldn't have a charge. Then, just like it's gonna be the region around the charge that if you will put a test charge is gonna feel, the electric force. And therefore, usually, if I will talk about the idea of an electric field, I will say, let's say I have here a positive, let's say Q charge, and then I wish to find something about the electric field here. I'm gonna just imagine that there is a very small charge that it will not disturb the electric field of this bigger charge here. And then I will ask myself how that test charge is gonna feel, or what is gonna feel, and then is gonna feel a repulsion force that is gonna be in this direction, and therefore I will say this is the electric field felt by a test charge here, or what is the electric field here. And if there is a negative charge, again, my test charge is going to be located here, and what's going to feel is going to feel what? It's going to feel the electric, field is going to be in this direction. Okay, then now here, if I have just one charge A here, and P is a point that is where you're gonna feel the electric force, then we can say that A modifies the properties of the space at point B and have that what is called the electric field. The electric field, it is defined as the force per unit charge exerted by point A on a test charge at P. Therefore, we're gonna say E, it is the force divided by Q. Therefore, its unit, it is a Newton per coulomb. And of course, I can also use Coulomb's law to find what is going to be the magnitude of the electric field. Now, if you have a positive charge here, you're going to find that E is going to be to the right, and if I will put a charge here that is positive, is going to feel a force that is going to be in the same direction. If the charge that I'm going to put at this point P is going to be negative, then the electric field and the force are in opposite direction. This is very important whenever you are going to talk about forces acting on charged particles like electrons, protons, or whatever. Now, here we are talking about the electric field of a point charge, and this is what I was talking to you about. Then I would say the electric field is gonna be a vector that is away from the charge, and if it is negative, is gonna be the opposite way. Now we can calculate the electric field of a point charge, and that is using Coulomb's law. If we will say E equals F divided by Q0 or by Q, then you're gonna have E equals that constant, the K electric. Like I like to use that notation more, K Q over R squared. And this is, the unit vector where is going to be the direction. And of course, the constants are similar to what I introduced before. Now, for calculation of electric field, and now here I will say this is for a point charge. Now we are going to study how we're gonna find for a distribution of charges, and I will say Coulomb's law is good for point charges, but maybe we are going to get a better way of calculating the electric fields for distribution of charges in chapter 22, where we are going to talk about Gauss's law and the idea of the electric flux. Here is the problem solving strategy for electric field calculation, where I will make a drawing showing the locations of the charges and also my coordinate axes. I will I should have consistent units. Distances, they should be in meters. Remember, here we are dealing with the newtons or newtons per coulomb. Then the conversion are really very important. Don't include any let's say centimeters or millimeters. The charges also, they should be converted into coulombs. Distinguish between the source point S and the field point P. The field produced by a point charge always points from S to P if the charge is positive, and from P to S, the source, then the charge is negative. Well, of course, again, we are going to use the addition of vectors that we discussed in chapter 1. And sometimes you will be able to have you're gonna have symmetries where you can cancel some of the components, and we will be able to deal with this case by case. If the charge distribution is continuous, define a small element of that charge, and then we will find the dE, which is the electric field because of that, and then we are going to integrate, and we are going to talk about this in a little bit. This is how we map the electric field of a point charge, and then I will say a point charge is going to produce an electric field to all points in space, and the field decreases by increasing the distance. And also the density of the lines, they're gonna tell you something about the strength of the electric field. Also, I will say the electric field lines, they point away, radially away from the charge. I want to go maybe first over the second one for the negative charge. Where again it is radially but it inwards, and also the field strength decreases as we are really increasing the distance, and also the density of lines is going to reflect something about the magnitude. Now the total electric field at a point is the vector sum of all the fields, as I did show you this, and then if I have here two charges, now the electric field that is resulting from Q1 is going to be in this direction, and the electric field that is resulting from E2 is going to be in this direction. And therefore, I will say, I can say that the total electric field is the resultant of these E1 and E2. Also, I want to go back here first. I want to maybe talk a little bit about this example before the other one, because this is going to show you also a sample of work where we are going to talk about other forces that they may be involved in this calculation. For example, here I have a 12.3 gram plastic ball that is tied to a very light 28.6 centimeter string that is attached to the vertical wall of a room. A uniform horizontal electric field exists in this room when the ball has been given an excess charge of negative 1.11 microcoulomb, you observe that it remains suspended with a string making an angle that is 17.4 with the wall. Find the magnitude and direction of the electric field in the room. Okay, here this is one of the examples where I need to actually talk about, you know, the free body diagrams, talking about also, you know, all the other forces acting on the object. And here, what I have is, this is my X, this is my Y. I have the tension making this 17.4 degrees. I have mg, and also I have the F electric in this direction. It is a negative charge. No, if it is a negative charge, okay. Yeah, I'm gonna say that the force is gonna be in this direction, and then here, what I can see from the electric, yeah, this is the force. I'm talking about the force. Okay, and just this is the force, and then I can say that the force electric should equal that X component of the tension, and that is T sine 17.4, and also mg should equal T cosine 17.4. If I will divide 1 by 2, then I'm gonna get this, and I will be able to calculate the force, the electric force, and that electric force is going to be Q times E, and then I can calculate E as F over Q. And remember, because it's a negative charge, then the electric field should be to the left. Also, if I will say whenever I'm gonna have like electric field lines that they are really curved like this, the electric field at any point is gonna be the tangent. Now this is the electric field lines of a point charge. Positive, this is when I have an electric dipole. Dipole means I'm gonna have di from two. I'm gonna have a positive and a negative, and this is really something that we are going to learn also in the lab. If I have two positive charges, this is the electric field that is gonna be, you know, for two positive charges. I will say the water molecule, it's an electric dipole. This is because of the difference in electronegativity of the oxygen and the hydrogen. And this is gonna be resulting in a net negative charge on the oxygen and a net positive charge. They are very small, but they are there. And therefore is going to be, you know, an electric dipole. And when dissolved in water, the salt also is going to be positives and negatives, and therefore is going to be attracted to the opposite charge, you know, I would say from the water, and therefore water, it is an excellent solvent. For this video, I'm gonna stop here before I'm gonna introduce the electric field of a distribution of charges.